This first mini-lecture for Chapter 7 introduces VSEPR theory, a method by which we determine the 3D shape of a molecule from its Lewis structure. VSEPR, or VSEPR, stands for valence shell electron pair repulsion. And the basic concept is that regions of electron density around a central atom, such as bonding regions and lone pairs, will repel each other due to the like charges of the electrons contained in these regions. Remember that electron repulsion is a destabilizing force, meaning it raises the energy of the molecule. Therefore, the molecule will seek to achieve the most stable 3D structure with the lowest possible energy by assuming a geometry that minimizes repulsion between lone pairs and bonding regions. Determining the correct 3D geometry for a molecule will involve counting the number of lone pairs and bonding regions, referred to as electron groups or domains. The Lewis structure of a molecule shows exactly how many electron groups surround each central atom and provides our starting point for determining the geometry of the molecule. So, it's crucial that you are comfortable in determining the Lewis structure for a molecule in order to be able to determine the geometry. The images below show the most stable geometries for central atoms with anywhere from 2 to 6 electron groups. Balloons make a great demo of the stability of these structures, as the balloons naturally repel each other when they press against one another just like electron groups, causing them to spread out as much as possible. If you start with the case of 6 balloons on the right, which gives an octahedral geometry, and then sequentially pop one balloon after another, the balloons will automatically reconfigure themselves to spread out as far apart as possible, and the structure almost appears to snap into the new geometry on its own every time a balloon is popped, showing how stable these structures are. You can watch a demonstration of this by going to the link below. The names of the geometries come from the names for polyhedrons. Note that octahedral gets its name from the 8 sides on the octahedron rather than the 6 vertices or 6 electron groups that we'll discuss for these types of structures. We'll discuss examples of each of these geometries over the next few slides. Linear geometries occur when there are 2 electron groups around a central atom. In the case of beryllium chloride below, the 2 single bonds on the beryllium lead to a linear geometry for the molecule. Note that there is a 180-degree angle between the 2 bonding regions, which is the farthest apart any 2 electron groups can ever be. All types of bonds count as just one electron group, which is why I've been referring to them as bonding regions instead of just saying bonds. This means that carbon dioxide, CO2, which has 2 double bonds, has just 2 electron groups and not 4. And hydrocyanic acid, which has a triple bond and a single bond, also has just 2 electron groups. Therefore, we don't just count the number of bonds around a central atom, but we want to count the regions where bonds of any type, single, double, or triple, are located. Since both carbon dioxide and hydrocyanic acid shown below have just 2 electron groups around the central atom in each, then these 2 structures are both linear with that 180-degree bond angle that is typical to this type of geometry. Trigonoplanar geometries occur when there are 3 electron groups around a central atom. Again, this can be 3 single bonds, as in the case of boron trifluoride on the left, or it could be 2 single bonds and a double bond, as in the case of formaldehyde on the right. Both of these structures have 3 electron groups, so they have the same trigonoplanar geometry. The trigonoplanar geometry gives bond angles of about 120 degrees between all bonds, but note that the bond angles in formaldehyde on the right are slightly distorted. This is due to the increased repulsion of the double bonds, since it has 4 electrons instead of just 2. This repulsion pushes on the single bonds to the hydrogens, causing their bond angle to decrease at the expense of increasing the bond angle between the oxygen and the hydrogens. However, be careful about structures that exhibit resonance. Since the double bond in the nitrate ion is delocalized across all 3 bonds, then these bonds will repel each other equally, so the bond angles will be all the same despite the fact that this resonance structure for nitrate contains a double bond. Also note that the trigonal planar geometry is, well, planar or very flat. This side view of formaldehyde below shows this. Similarly to how the double bond has increased repulsion due to having more electrons, lone pairs also have increased repulsion due to the shape of the electron cloud on a lone pair, which is broader than the shape of the electron cloud on a bonding pair. When lone pairs are present on a central atom, we also need to make a distinction between the central atom's electron geometry versus its molecular geometry or shape. The electron geometry gives the geometrical arrangement of the electron groups, which includes lone pairs and bonding regions. But the molecular geometry or shape gives the geometrical arrangement of just the atoms and basically ignores the lone pairs. The sulfur dioxide molecule SO2 below has a trigonal planar electron geometry since it has 3 electron groups, 1 single bond, 1 double bond, and a lone pair. The presence of the lone pair means that the molecular geometry is not trigonal planar, but is instead referred to as bent. Looking at the 3D pictures for both the bent geometry and the trigonal planar geometry, we can clearly see that they look different when we only consider the atoms. However, note that the bond angle between the atoms is still 120 degrees, as we would expect for a trigonal planar electron geometry. So even though this molecule only has 2 terminal atoms, just like in a linear molecule, it has a bond angle between them. It has a smaller bond angle between them than a linear case due to that lone pair, which means that this is still part of the trigonal planar electron geometry family, even though we call the molecular geometry bent. Tetrahedral geometries occur when there are 4 electron groups around a central atom, as in the example below for methane. Tetrahedral structures will have a 109.5 degree bond angle the whole way around the structure, as these are very symmetric molecules. The tetrahedral electron geometry family also includes 2 additional molecular geometries when 1 or 2 lone pairs are present, as seen here with ammonia and water. Note that both ammonia and water have 4 electron groups around the central atom, indicated by their Lewis structures. Ammonia with 1 lone pair has a trigonal pyramidal molecular geometry, but will still have bond angles close to 109.5 degrees due to being part of the tetrahedral electron geometry family. However, the bond angle is a little less due to the increased repulsion by the 1 lone pair. Water with 2 lone pairs has a bent molecular geometry, but will still have a bond angle, again, kind of close to 109.5 degrees due to being part of the tetrahedral electron geometry family. Again, the bond angle is a little less due to the increased repulsion by the 2 lone pairs. Also note for water how the way you draw the Lewis structure can actually suggest the bent structure versus a linear structure, which would be incorrect for this molecule. Trigonal pyramidal geometries occur when there are 5 electron groups around a central atom, as in the example below for phosphorus pentachloride, or PCl5. Note that this structure is the first with an expanded octet, having more than 8 electrons around the central atom, which will always be the case for trigonal bipyramidal electron geometries and octahedral geometries, which we'll talk about next. Therefore, central atoms from the first and second row will never display these geometries. Trigonal bipyramidal structures have 2 different bond angles. The bond angle is 90 degrees between the axial position and an equatorial position, but the bond angle is 120 degrees between 2 equatorial positions. This is easiest to see in the top-down view of the molecule on the right, which shows that the equatorial positions take on a geometry that is very similar to trigonal planar. The difference in bond angles is important when considering where lone pairs on the trigonal bipyramidal electron geometry will be most stable. Lone pairs repel more than regular bonds, so they will want as much distance between them and the surrounding electron groups as possible. This is best achieved by placing the lone pair in an equatorial position where it will only have 2 90-degree angle repulsions, whereas if it was in an axial position, it would have 3 90-degree angle repulsions. The 120-degree angle is broad enough that there is minimal repulsions between the lone pair and the other electron groups in equatorial positions. Finally, this results in the seesaw molecular geometry for sulfur tetrafluoride, or SF4, which is part of the trigonal bipyramidal electron geometry family. Now, if a second lone pair is included in a trigonal bipyramidal electron geometry, then the lone pair will again appear at an equatorial position, and this leads to a T-shaped molecular geometry, as is the case for this bromine trifluoride molecule. If a third lone pair is included, again in an equatorial position, this leads to a linear molecule geometry. So the trigonal bipyramidal electron geometry family has 3 molecular geometries with lone pairs: seesaw, T-shaped, and linear. Finally, octahedral geometries occur when there are 6 electron groups around a central atom, as in the example below for sulfur hexafluoride, or SF6. The octahedral geometry is incredibly symmetrical, with all 90-degree bond angles the whole way around the structure. So, when the first lone pair is introduced into the octahedral electron geometry, it doesn't matter where it is placed, as the bond angles will be the same for every position. This results in the square pyramidal molecular geometry for bromine pentafluoride. When the second lone pair is introduced into the octahedral electron geometry, it is placed exactly opposite the first lone pair, as any other position would put them at a 90-degree angle from each other, which would be incredibly unstable due to the repulsion between them. By going into the position opposite the other lone pair, this minimizes the repulsions and leads to the square planar molecular geometry, which is also very flat, like trigonal planar is. When assigning geometries to molecules with multiple central atoms, only consider the electron groups around each central atom individually. So for methanol shown here, the carbon atom has 4 electron groups, all of which are bonds, so it has a tetrahedral molecular geometry. The oxygen atom also has 4 electron groups, but 2 of them are lone pairs, so it has a tetrahedral electron geometry, but a bent molecular geometry. Here's an example with 4 interior central atoms. Note that 3 out of 4 of these central atoms have 4 electron groups, yet they all have different molecular geometries due to the difference in the lone pairs. Note that the rightmost carbon only has 3 electron groups, so this is the only central atom in this structure with a trigonal planar electron geometry. Across these slides, we have seen the 3D representations of these geometries, but in order to draw these structures in 2D on paper, we need a way to represent the 3D structure easily. This is done with hatched and solid wedges. When a straight line is used for a bond, this is meant to imply that the bond is parallel to the plane of the piece of paper. If a hatched wedge is used for a bond, this indicates that the bond is going into the page or away from the viewer. Whereas if a solid wedge is used, it indicates the bond is coming out of the page or towards the viewer. Spend some time to note the differences in this notation for some of the 3D molecular geometries shown below, and also note how the flat or planar structures are drawn totally in the plane of the page with solid lines for the bonds and don't need to have any wedges. In summary, the 3D shape of molecules is determined by counting electron groups around central atoms in the Lewis structure, so it is crucial to start with the correct Lewis structure. Lone pairs count as 1 electron group, and any type of bond, a single, double, or triple bond, all count as only 1 electron group each. Repulsions between these electron groups dictate the geometry, and repulsions are greatest between 2 lone pairs and weakest between 2 bonding pairs. Repulsion also increases with the types of bonds being greater for double and triple bonds. These differences in the repulsions can lead to a slightly distorted geometry and bond angle when the electron groups around the central atom consist of a mix of single, double, or triple bonds or lone pairs. This concludes the first mini lecture for Chapter 7. Please note any questions you may have about this material and how it is utilized to solve problems in the sapling homework or end of chapter exercises for this chapter. Please post any urgent questions on Piazza. I will also take questions on this material during one of our virtual class meetings, and during that time we will focus more on problem solving for concepts in this chapter.